Welcome to today's session. We will be starting Unit 5, that is Synchronous Motor Drive. Before starting the unit, I strongly recommend you to please go through your machines book for better understanding. So let's start. As you all know, synchronous motors are doubly excited machines. That means it has we give three-phase supply to the stator and DC supply to the rotor, which provides the field. The commonly used synchronous motors are wound field synchronous motor, permanent magnet synchronous motor, synchronous reluctance motor, and hysteresis motor. We will be discussing more on wound field synchronous motor, which has a DC field winding which is supplied from a DC source through slip rings and brushes. The commonly used wound field synchronous motors are cylindrical rotor motor and salient pole motor. It is distinguished depending upon its rotor construction. Cylindrical motor have higher mechanical strength and are employed in high power and high speed applications. And in other applications, we use salient pole motors due to its low cost. Let's discuss the working of synchronous motor. As said earlier, synchronous motor is a doubly excited machine. That means three-phase supply is given to the stator and DC supply is given to the rotor. When three-phase supply is given to the stator, a rotating magnetic field is produced. Let me represent it by a vector called Bs. When DC supply is given to the rotor, it produces a steady state magnetic field. I will represent it by Br, another vector. Now, Br will always tend to chase Bs, which in turn is continuously rotating. That means Br will always be trying to catch up with Bs, which is continuously moving with a speed of synchronous speed, and hence the rotor will tend to move. Next, we will be discussing equivalent circuit of cylindrical rotor motor. This is the equivalent circuit. Please note that here I have not shown the field circuit. As well, the resistance is also missing because excess is comparatively very high compared to resistance. Hence, we are further simplifying the per phase equivalent circuit of the cylindrical motor. I have represented the stator voltage V angle 0 and E is the excitation EMF, and it is written as E angle minus delta. It is so because the difference between the vector V and E is phase difference between V and E is delta. Excess is synchronous reactance. As you all know, the power input will be then 3 into VIS cos phi, where cos phi is the power factor and phi is the angle between phase angle between IS and V. If the stator losses is neglected, then the power developed will be same as the power input. So we can write Pm equal to 3 VSIS cos phi. If you further solve for Is cos phi, you will get Pm as equal to 3 VE by Xs into sin delta. Now, as you all know, torque is equal to Pm by omega n. So if you further divide Pm by omega n, you should get the torque equation. Hence, this is the torque equation. Let us study the speed torque characteristics of cylindrical rotor wound field motor. The speed torque characteristic is same for salient pole motor also. Please note it. So the speed torque characteristics for both the motor are same. In the figure you can see that the speed is constant at omega ms, which is the synchronous speed, because synchronous motor rotates at a constant speed called synchronous, which is nothing but 4 pi f by p radian per second. Now it works in two modes, braking as well as motoring mode. You can also see that the speed is constant till the maximum torque called pull out torque. After this torque, the speed won't be constant and the machine will pull out of its synchronism. So in order to prevent damage due to excessive current, automatic air circuit breakers are provided to disconnect the machine when it comes out of synchronism. But till Tmax, whatever the load is, the speed will be constant, that is omega mx. Now the next question is, when will the motor work in motoring or in braking operation? The motor will work in motoring mode when the angle, when the voltage E lags the stator per phase stator voltage V. Similarly, it will work in regenerative braking when E leads V. Hence, the motor can work both in motoring as well as in braking operation. Let's study the phasor diagram for cylindrical rotor motor. So I will redraw the equivalent circuit, and you know that V will be equal to E plus IS XS. So for lagging power factor, if we were to draw a vector diagram, then first I will draw the voltage V. Now you know that the angle between V, since it is lagging power factor, IS will be lagging V by an angle of phi, which is the phase angle. So I can draw IS lagging behind V, and the angle between the two is phi. Next I will draw E, vector E, and you know that the angle between E and V is delta. Now if I were to draw ISXS, it has to be perpendicular to IS. So this is ISXS vector. So if I want to add it with E, I have to draw a line, a vector parallel to it. That means in this way. Hence you get V, which is equal to E plus ISXS. So this is the phasor diagram for lagging power factor. If we were to draw for unity power factor, we know that phi is 0 over here. So first I will draw V, and since phi is 0, IS will also be on the same line. Then I can draw E, which will be in this way. Now again IS XS will be perpendicular to IS, and I can add it with E in this way, and hence again we will get V is equal to E plus IS XS. Similarly, we can draw for leading power factor also. If we draw V in this way, now IS is leading the voltage V. So it has to be drawn in this way. Angle between them is phi. Now we can draw E, angle between them is delta. Again we can draw IS XS, which will be perpendicular to IS, and if you add it with E, you will get a vector like this, which is equal to V. Hence we can draw the three phasor diagram for lagging power factor, unity power factor, and leading power factor. So when excitation is small, the machine operates in lagging power factor. If you observe, when the excitation EMF E is small, the machine operates in lagging power factor, and the power factor can be made unity or leading by increasing the field excitation. So the important feature of wound field motor is that its power factor can be controlled by varying the field current or E. So with this we come to the end of this session. Thank you.